This is a beginner-oriented talk. So if you're not a beginner, you might want to go to David Steele's talk instead. Or I don't remember what's in the third track. We're going to be going over what EXPLAN is, what it does, how to use it in brief. If you already know those things, then go to another talk or spend time on your email. So let's get started. A little bit about what EXPLAN is. From people, some people are used to tools in other database systems. Some people are not used to tools at all. And some people have some misimpressions about what EXPLAN can do. So the things that EXPLAN does do is to actually show you how the query planner has decided to execute a particular query. And depending on settings, give you stats on how the query actually got executed. Those stats can actually give you some idea of why a query was slow. And particularly, you identify which step in the query took the most time, because often it's not the one that you would intuitively believe. Now, EXPLAN doesn't do everything for you, though. For example, a lot of the big questions you actually get is, hey, I have an index on X. Why didn't the query use it? EXPLAN won't tell you that, at least not directly. It won't tell you how to rewrite your queries to make them faster. It definitely won't identify any of the other factors that makes the database can make a database request slow, things like network lag, et cetera, including not showing you any sort of time that took place outside the database, which can sometimes be much longer than what's taking place inside the database. So in order to actually understand how EXPLAN works, you have to understand a little bit about how the query planner works, because EXPLAN is really just a bunch of text output from the query planner. So what happens is when you send Postgres a query, after it's been parsed and reduced to a canonical parse tree and everything, then the planner basically breaks down steps of the query into individual nodes. And then it figures out the different ways that each node could potentially be executed. And then it'll chain all of the combinations together that actually will work as combinations into plans. Now, each one of those nodes is going to have an estimated cost. And so then it'll add up the cost of every different possible combination of plans into a bunch of sets of different plans, each of which is a different cost. And then it'll pick the plan with the lowest overall cost. I've been told by some of the original Postgres developers that our query planner was originally written in Lisp. It certainly feels like it was in terms of how it works. So now, to understand what I mean by node is that basically what happens with a query, with a query planner node in theory and with a query executor node in reality is that you have this node operation. And two things go into node operation. One or more row sets that are coming from some other step of the query or from storage, and some parameters. And then what it's going to output is another row set. So for example, if we have a sort node, you're going to have, say, rows coming from a table scan going into the sort node, and a set of columns that we're going to sort on and how we're going to sort them as parameters going to the sort, and then sorted rows will be coming out. And the reason, this node concept is expressed in what you see when you look at an EXPLAN plan, is that each one of the sections of the EXPLAN planners will be going over is actually a representation of one of these nodes. Because what happens is the query planner plans the node, and it outputs a bunch of text as to how that node was planned, and then it moves on to the next node. Now, I mentioned here a couple of times cost. So the cost figure is an arbitrary calculation in which Postgres estimates how expensive a query will be to execute mostly in terms of time, but a little bit secondarily in terms of system resources. But more we're concerned about response time. And it's important to understand that this cost is only meant to be self-referential. That is, it should be consistent, if the query planner is planning correctly, then query plans with a higher cost will take longer to execute for that particular query. But that doesn't mean that costs between queries are actually comparable, except on an order of magnitude basis. And it doesn't mean that there's any sort of linear scale by which that cost is comparable to an amount of milliseconds spent in execution time. Now, some people actually like to spend time monkeying with the sequential page, the sec page cost, sequential page cost parameter to try to get the cost figure to match up with milliseconds execution time. This is unlikely to be successful, but I know that people do it. So let's actually look at a query plan for something. This is the default explain output. So here we've done explain here. And we're just doing a simple primary key lookup on a table. And this brings us up in EXPLAN. We're going to do an index scan on the primary key, and we've got some cost figures there, and conditions and several other things. So it's actually, now that's the explain. So this says, hey, given this query, we're going to do a primary key lookup. Given this query, here's how I'm planning to execute it. I'm going to look at the primary key index, and I'm going to scan the primary key index, and I'm going to return an estimated one row based on the scan of the index. A reasonable plan. Now, we can get more information out of explain, though. The first thing is to do explain analyze. So there's actually, sort of two major versions of explain. Explain just says, tell me how you would execute this query to the planner, right? Explain analyze says, tell me how you'd execute this query, and then execute it and tell me how you did. Now, it's really important to know that explain analyze does actually execute the query. So if you're analyzing a data writing query like an update or insert or delete statement, it will actually perform that update, insert, or delete. So if you don't actually want it to modify your data, then you'd better wrap that in a transaction and roll it back after it's done. So when we actually run an explain analyze on the same query, we get some more information. We actually get a bunch of timing information, which we can sort of match up with cost, right? Which is, we said, okay, well, we expected it was going to take, our cost is fairly low, it's 2.5, and it actually took 0.28 milliseconds. And we thought we were going to look up one row, and we actually did look up one row. And here's our index condition. And also, as of 9.4, which is what I did this on, we also get some more information, which is to say, hey, how much time did the planner spend planning this query versus how much time did it spend executing this query? Because on 9.3 and earlier, you didn't get the planner time at all. And so if you had a query that was particularly difficult to plan or particularly easy to execute, you got a deceptive total execution time. Because as you can see here, that the planning time was actually twice as long as the execution time. Because the execution time was very, very fast. This is an in-memory table, and we're looking up something by primary key. You want to actually, that's one of the big benefits of 9.4, and you want to actually look at that planning time there if you're on 9.4 or later. And if you're not on 9.4 or later, this is a good reason to upgrade if you have to do a lot of slow query troubleshooting. So that actually gives us sort of where to execute. So this means that most of the time, you want to run explain analyze. Like one of the first things, people come to the performance list and they give us an explain. Why is the query being executed this way? First thing everybody says is, can you give us an explain analyze on that? The reasons not to run an explain analyze, number one, the query never finishes. So you can't run an explain analyze because you run it and it hangs forever. Or you're monkeying around with indexes and you just want to say, hey, would this index be used if I created it? Or you're checking for partition tables. You're checking to make sure that the query that as you're running it is not going to hit all the partitions. In that case, you just need explain. Otherwise, you really want to be running explain analyze. There's a whole bunch of other explain options now. I go over a few of them: buffers, costs and timing, format, verbose. These parameters actually get passed by the extended syntax. So you do explain, and then you open parentheses, and then you do a set of parameters with on or off or the parameter condition, as I've got in that format there. The one I will go over, costs and timing are on by default. So if you actually look at our explain plan here, right, this is costs, and that's timing. Now, by default, we return those, because that's what you want to see most of the time. We added the timing off option, mainly for platforms like Windows in which checking the system clock is very expensive. And for that reason, when you run explain analyze, if you're displaying timing, it can sometimes be deceptive how long it will take to execute because checking the system clock takes so long. Obviously, you're getting a lot less information that way, though. And honestly, I think costs as a parameter, the ability to turn costs off is just for completeness. We gave you the ability to turn everything else off. We might as well add costs off. I don't know what you'd use that for, but it's there. However, buffers, format, and verbose are all useful. So let's actually show a couple examples. So here's an example of doing another query actually with buffers. This is a giant JSON table with 20 million JSON blobs in it. And I do a search on this, and I'm doing a JS query, and it's doing a bitmap index scan and that sort of thing. I'll explain what that is later. But the important thing here that we get out of buffers here is we get these two statistics that say how many buffers we accessed that were already in Postgres's dedicated cache, and how many buffers had to be read from the file system. Now, the red figure, for those of you who are familiar with Oracle, are what are known as logical reads, not physical reads. That is, we're requesting these from the file system, but they may be in the file system cache as opposed to being need to read off of storage. Postgres doesn't actually know whether they're coming from file system cache or whether they're coming from your actual disks. It just knows whether or not stuff was in Postgres's cache. But in a lot of cases, if that red figure is really high, that can be an indication of why a particular query is taking a really long time, because we had to swap in a whole bunch of data from the file system or the file system cache into Postgres' dedicated cache. And if it's a large enough amount of data, we have to swap it back out again. Whereas if you have a high buffered shared hit, if everything's in Postgres' dedicated cache, then you can kind of eliminate the idea that reads from the file system are the slow part of executing this query. We can also reformat queries. So this format, our default format here, which I'm using through this out example, is a little hard to read. It produces very long lines. They wrap oddly. A lot of these things are going to be in one line. I'm actually wrapping them for the slides to make them readable. So it has these really long lines. It has the indentation format that's actually quite hard to read. So we added some other output formats. The one that I actually find the most useful for human reading is YAML, because it takes all of those criteria and breaks them down into individual criteria and lines here, right? So instead of having index scan, et cetera, this sort of thing, we're actually getting individual key value pairs. Index scan forward, patrons, alias, startup cost, total cost. It's actually a little bit easier to show you on the console here. So like say we actually plan out this join, and we're doing a query plan like this, we've got all these really long wraparound lines that can be a little hard to read. So let's actually change the format to this. Need a comma? Hold on. So if you look at this, then we actually break stuff out into individual lines. And it's a lot clearer what we're doing in each node, because you can actually read it vertically. Now, YAML is a little bit more human readable, but if I'm going to actually process this with an automated script, like say I'm looking for query plans that are actually going to hit a particular table, then I'll actually use something that's a little bit more machine readable. Like, for example, JSON. Not as nice to read as a human being, but lots more parsable for script code. So something to keep in mind for your use of explain plans. I'm going to be showing the default explain plan format for the rest of this presentation because I'm trying to jam stuff on slides. But when I'm actually looking at a lot of these things, I actually like to use the YAML format to break it out. So second option here is verbose. And verbose only adds really a couple of things to your query. The main thing that it adds is this output portion that says for each node, like I said, each node takes a couple of inputs and it has one output, which is a row set. So this shows you what the row set is that's being output. which can be really important when you're actually trying to figure out certain performance issues. Like for example, if the inner node was actually outputting a row set that was, say, 800 columns wide, Postgres has a certain performance issue that it hits when the columns won't fit on a single 8K data page, either in memory or on disk. And so even if you're not returning 800 columns in the final query, if you're using 800 columns internally, that can actually slow things down. So that can be good to know. It's also even more, the other thing that verbose does is if you've been using aliases for some of your tables, it will de-alias those so that you can actually see which tables are associated with which columns, so that if you're looking at the whole thing of, hey, this is really slow, why is this not indexed, it's actually a lot easier to see from the final output what table that column was actually originally related to. So your main sort of useful options. So let's actually delve into what that output means on a detailed level. So the first thing to understand is how that execution plan goes, which is that EXPLAN is, because of the way that node output works, it's an inverted tree. That is, the innermost portion is the one that was executed first, for some definition of first. And what I mean by for some definition of first is there's a certain amount of concurrency here, particularly when we're waiting on I/O. Like if we're waiting on I/O for a scan, we might start processing the rows coming in from that scan at a higher level node while we wait on the I/O. And particularly, so the second thing is then this gets executed, right? So here we've got at our base, the inner thing, the first thing that gets executed, quote unquote, first, is this bitmap index scan on lone patron, which is an index, right? And so then we're actually going to do two things which may be done concurrently. They actually are done to some degree concurrently, which is to do a bitmap heap scan again on loans. And so this is where we did a bitmap index scan, and that's where we scan an index. And well, I'll talk about what these nodes mean later. We did a bitmap index scan where we scan the index to match it up against the filter criteria. And then we actually need to recheck that against the actual table storage in order to check visibility rules. So that's going on, and the index scan on the patrons table is going on kind of at the same time. And then finally, we actually do a join between the two of them, in this case a nested loop join, which is a good plan when you're returning a very small number of rows. So let's look at what's in one of these individual node output sections. So in the default thing, this is actually all in one line. I've broken it out again for readability. So the first thing is that it tells us what operation it's doing. What kind of node is this? It's an index scan, and it's using the patron's p key index on the table of patrons. So it tells us what am I doing in this node. And then the second thing here is it'll give us our cost figures. Now if you're doing explain and not, this comes in whether you're doing explain, analyze. And so you'll notice, interestingly enough, that this cost figure is a range. So what does that mean? Why do we have two numbers here for cost? Well, the answer is that's actually the cost of returning the first row versus the cost of returning the last row. And the difference between the first row and last row can be important in certain query plans. In this one, it is not particularly, but it's there. And so the cost you generally sort of care about is that ending cost. But the startup cost can be important if it's large. Like in this case, for an index scan, the startup cost is not going to be large. But when we go up to higher level things like a hash aggregate, the startup cost actually is large because you have to create a hash table. Then how many rows do I expect to return? One in this case, right? And the width is how large is that row? And that's based purely on the Postgres statistics, where we estimate what's the average size of a row in this table. Again, important when it's unusual. Like if that width is like 480, then you know that you actually have very wide rows and that maybe some of any performance problems have to do with the fact that those rows are very wide. Then if you're wanting to explain analyze, you'll get how did we actually do? So now again we have two time figures. In this case they're identical because we're only returning one row. But if we were actually scanning hundreds or thousands of rows, again you would have how much time did it take to emit the first row from that node versus how much time did it take to emit the last row. Then we have, again, the number of rows, which turns out, in fact, to be 1, and the number of loops. Now, what is this loops thing about? Well, so in some plans, you actually will loop over a result set. Most of the time, this is because you're doing a nested loop join between two tables. Nested loop join is the simplest kind of join that says, for every value in this table, we are going to loop over, we're going to request all of the matching rows from this other table. It's the best plan when you're expecting to access very few rows. It's a terrible plan if you're expecting to access a lot of rows. The reason it works for very few rows is that it has almost no startup cost. So, and the thing is, that loop figure actually becomes important if you're going to be going through a lot of loops, right? Because say we had 1,258 rows from table A, and now we're going through 1,258 loops to get the rows from table B. Well, when you're doing loops, this time actually means something different. When you're doing loops, this time is actually the average time to return a single set of rows from the loop. And so you actually have to multiply the number of loops times the average time to see the amount of time you spent total on getting data from that particular table. And then the final thing that we'll get is we'll optionally get a set of conditions. These are basically the parameters that got passed into the node to do the thing we're doing. Like in this case, it's the primary key lookup we're doing, right? This is the card number that we're looking up as our index condition. And again, this is a useful thing to look at because when you're saying, hey, maybe I need an index there, you want to look at this set of conditions to say, hey, where would an index be useful, right? These are the conditions we're doing. Should I be indexing for all or some or all of those conditions? So now I've gone over these sort of internal rows. So now let's actually talk a little bit about the different types of nodes that we have. I've mentioned some of them already. There are actually a lot of them these days. So our first sort of basic node is scans. Postgres has 4 different kinds of scans. And what scans do is, let's retrieve data from some external data source. Usually a scan is, let's get data from a table or index. There are other things, like in cases where you might be we'll talk about materializing, talk about materialized nodes later on, but if you have a materialized node further on, you may then do a scan over that materialized data set. But most of the time we're talking about actual tables and indexes. So CTEScan is a cryptic term for full table scan. That is, anytime you see CTEScan, you should know that Postgres scanned the entire table in order to find whatever you're finding. Again, that's a good plan if you needed most of the table. And it's a bad plan if you only needed 1% of the table, and it's scanning the whole thing anyway. Now, if you only need 1% of the table, hopefully you can use an index, and then you might be doing an index scan. So an index scan is a standard. We're going to do a transversal of the index, like a transversal of the tree if it's a B tree index, and look for things that match whatever conditions that we have. And so, a good thing if you've got the right index. But we've got some other variations on index scans. One of them is the index-only scan. That is, if the data you're mostly looking at is old data, so it is visible to all users because nothing's been updated recently, then you can do what's called in 9.3 and later? Yeah, 9.3 and later. You can do what's called an index-only scan, where with a regular index scan, we actually have to check the table to check visibility rules. But if we already know that everything in the table is visible to all users, then we don't have to check the table, and we do an index-only scan, which is going to be slightly faster because we don't have to check the table. Or if we think we're going to go ahead and take the conditions from that index and match it up against other conditions, then we might do what's called a bitmap scan. And that's where we scan so there's actually 2 kinds of bitmap scans. That's where we scan in a bitmap index scan, we scan the index and we construct a bitmap of matches the condition, doesn't match the condition. And that's a way we can, for example, say combine index scans of 2 separate indexes into a single query by combining the bitmaps. Now, usually when you see the bitmap scan, like I showed you in my example, you will get a bitmap scan followed by a bitmap heap scan, because again, we need to check visibility rules on the table, which is only stored in the heap, which is another name for table storage. And you will often see another thing called the bitmap recheck, which is, again, checking for rows that may have changed recently to make sure that they still meet the condition that we applied the bitmap scan to. Now, most of these scans are going to contain a filter condition, because unless you're just doing select star from table, you're going to be applying a filter condition to that scan. So here's an example here with our bitmap. So we've got the bitmap index scan on the inner node. So we're doing a bitmap index scan for this index condition of card number equals that long number. And then that bitmap index scan sends rows up, and then we do a bitmap heap scan to make sure that all of the index nodes point to rows that are currently visible. And then we return that and move up to the next stage of the query. So once you've scanned some data, what is the other thing we're going to do with Postgres? We're going to join it, right? So again, the nest loop is the simplest kind of join. And this just says for every row in set A, look up the rows in set B, right? You'll see those a lot. Now a hash join is actually a little more complicated. Make a hash out of set A, and then match the groups of rows in set B against that hash table. This is going to be faster for large data sets, right? If I want to match 10,000 rows from this table against 1,000,000 rows from that table, a hash join is going to be faster provided I have enough memory for the hash table. So one of the things that influences whether a hash join is used or not is what you have workmem set to. Now the other thing that you might get is a merge join, because if I'm getting data from set A and set B, and that data needs to be sorted in the next step of the query, then Postgres might say, and set A and set B are mostly equal in size, like 1,000,000 rows from set A, 1,000,000 rows from set B. Then what Postgres may do is say, well, I'm going to have to sort these anyway, so I'm going to sort them ahead of time, and then I'm going to sort of zip them together in sorted order. And that's called a merge join. You won't see merge joins as often because the sort step is expensive, and so we're only going to do it if we know we're going to have to sort the data later anyway. But you will see it some of the time. Now, there are actually other kinds of joins. When was lateral join introduced? 9.4? Yeah, so 9.4 we have lateral join, which is generally a join against a table expression in the from clause. 9.2 or 9.3, I think 9.2 and up, we have semi-joins, which is a special kind of join that's generally used for an outer join where we know we're only going to match part of the data. And then we have the anti-join, which is for when you're doing things like not in or where not exists, or left outer join where null. And then we will do an anti-join, which you will see for that. So again, a couple of examples here, right? We've got a hash join here with all of its things, and you can see with the joins we get then, here's our condition. Instead of being like a filter condition, this is a what are we matching on for the join. And again, can give you some clues for where you might need to index things if stuff is slow. For the merge join, we've got that, and again, the matching the join. Particularly one of the things you want to look at for join conditions when you're trying to troubleshoot queries is if one of those two values is being coerced to a different data type, like if it's saying source.id : numeric, then you may find that indexes are not being used because your data types don't match. And so the fix for that is either to create a different index or fix the data types in the tables. Now, at the top level of the query, one of the things that you may see is aggregates. And what aggregates are for is, hey, I'm doing a group by, I'm doing a sum, I'm doing a count, I'm doing a standard deviance, whatever, in order to present information about the query. So the sort of default type is the group aggregate. This is a standard aggregate where we just flow through the tables, emit rows as we aggregate things. And this is what we're going to do in a very large data set if we don't have enough memory for a hash aggregate, because a hash aggregate actually constructs a hash table and then uses that to actually group stuff according to whatever our grouping rules are. If you have enough memory for that, that's almost always faster. So you actually see most of the time when you're doing aggregates, it will do a hash aggregate. Postgres will. And so if you see Postgres doing a group aggregate and the group aggregate is slow, it's taking a long time, again, one of the first things to think of is, hey, maybe I should increase work memory limits. Window aggregate, using for windowing queries. Otherwise, it's pretty similar to the other forms of aggregates, except that windowing queries work differently. And so that's a window ag node. So examples again, hash aggregate here, group aggregate there. Now in this case, the other reason to use a group aggregate is because we're actually operating over very few rows, and constructing the hash table isn't worthwhile if you're only aggregating 10 rows. And that's the case in this second example here. But the top example is more of what you would generally see for a hash aggregate, right? Now, one of the important things to know for the aggregate node is that the number of rows here that we're seeing is not the number of rows that was aggregated, it was the number of rows that was output. So if you want to see how many rows we're aggregating, you need to look at the nodes that are feeding up to this aggregate. So some other operations here that you will see from time to time, unique. This is mostly these days done for special deduplication of rows, particularly distinct, union, and partition merge, where we'll do the unique node. If you're actually doing some sort of unique operation like group by in aggregates, most of the time you'll see a hash aggregate. So you're not going to see unique nodes all that often. Sort node. Pretty obvious, yeah, we're sorting data, right? And then a limit node, which supports limit and offset. Other operations, a little less common. CTEScan. How many people here use common table expressions, otherwise known as with clauses? Yeah. So you see the CTEScan a lot. Right now in Postgres, any with clause gets materialized. It gets executed as a separate sort of subquery and not merged into the main query. So you will see all of these CTEScan nodes for every CTE that you have. Subquery scan, same thing but for subqueries. If we find that there's a subquery that it isn't effective to merge it into the main query, the first thing that we try to do is we try to merge it into the main query because it's going to be faster overall because it allows us to do more different kinds of plans. But say the subquery has a limit in it or it has an aggregate or something else, we won't be able to merge it in and then you'll see a subquery scan. Materialize. In some cases, particularly with subqueries that contain aggregates and other stuff, we can't collapse it into the main query, and we'll actually have to materialize a full result set in memory in temp space. That's actually generally a fairly expensive thing to do, so if you see that, that's often a case of this query needs optimization, but sometimes it's unavoidable with certain kinds of queries. And then append, which is where you're merging row sets for union, all, or for partitions. So examples here, we've got a CTEScan node example. And again, we're doing a CTEScan on whatever this toe-tab with clause is. Here we've got a cost estimate, which is off the charts, but it looks like it's accurate because that was also really slow. Because we were doing a whole bunch of filters on this. Because, for example, so again, this is only returning 4 rows from the CTEScan, but here we see, this is actually one of the useful things that you'll actually see. And by the way, this 9.3 and later, not available on older versions of Postgres. The rows removed by filter, really freaking useful and another reason to keep current with Postgres. This actually says, hey, this CTE actually returns 37,000 rows. But then when we did the CTEScan, we had to filter outside the CTE for extra conditions, and only 4 of the rows were compliant with the filter. Again, useful as a sort of a key to optimization. So when you're doing all of this, one of the things that you often actually want to figure out is, hey, why is my query slow? How does this relate to actually figuring out why my query is slow? Right? Just explain all of these things. We've got our nodes, we've got our plans, we've got our costs, we've got our other things. So let's actually look at a few common examples. Now, cut off the bottom here. So I actually want to introduce you to this site called explain.depesz.com. You know what? Let's just go there. So this is something written by Hubert in Poland. And it's this great site where you can actually just paste in your query plans. And it does a certain amount of highlighting in order to match common issues, particularly issues where there are two main issues, which is row counts don't match and estimates don't match. And you just basically sort of paste your thing in there, and then a whole bunch of PHP code actually tries to parse it and suss out some of this stuff. Now, I'm not pasting something in, but one of the other things that it does is actually it posts a history of the queries that have been posted on the site unless you disable the history feature. And that history can be fun to look at to see other people's bad queries. So this one is actually complicated enough to scroll off the screen. But you can see right here that it's actually, we've got two different kinds of highlighting here. One of the kinds of highlighting here is which things actually, which things actually had a very high response time, because this is time here. And the exclusive is just for this node, and the inclusive is for everything that led up to this node. And so then you can actually drill down and you can say, okay, what was the first thing that was really costly? And it's actually this was the first thing. This particular node was the first thing that was really costly. So actually, let's look at what that was. So we had this hash join here that was pretty costly between these two different things. Now, mind you, this hash join is actually returning. It's actually returning 93,000 rows. So there's reason for it to be expensive. And if you actually look down here, you look at what things fed up to that, right? So we have, I realize the text is kind of small. One of the reasons why I'm not showing all of my examples on EXPLAN is that you can't actually enlarge the text on this for the screen. So then you actually start delving down into what led up to this. So that's a derivative resource. The other thing that it actually shows you here, so one of the things it shows you is which things were costly steps, either inclusively or exclusively. So you see right here for this query plan that I'm showing, the bottom step that you can't necessarily read, that one is read in the inclusive column, which means that that step was individually really expensive, whereas the steps above it were only expensive because the steps below it were expensive. And then the other column is this rows X column, because one of the big things that leads to bad query plans in Postgres is, hey, is the number of rows the planner was expecting to get within an order of magnitude the same as the number of rows it actually got. When you see the query planner making a bad plan, most of the time it's because it estimated the number of rows wrong. Let's give a couple examples of sort of simple things that you see that are potentially a problem. So the first simple thing is, hey, queries that need an index. First thing we're saying is, hey, we're getting a sequential scan on this table that has 200,000 rows. That's probably a bad idea, particularly when we have a filter here and potentially a join against a table in another column. And so what this instantly tells you is, hey, I probably need an index on the other column I'm joining against, which you can't actually see in the example, but I probably need an index on the join column plus the category column. Because here we're joining 200,000 rows, we're actually getting 150,000 rows back, and we're eliminating 35,000 rows from the filter, and then we're going to be joining against something else. And that actually took a fairly significant amount of time, 500 milliseconds, half a second, which actually this total query, when I pulled it off of EXPLAN, depsays.com, the whole query was 800 milliseconds. So this is the majority of the time spent on the query. So that's one of the things we look for is, hey, are we doing a sequential scan against a large table? Then that's probably an indication that either you don't have enough indexes or the indexes you have are not the right indexes for the queries you're running or for that query. Another one here is bad row estimate. I've actually adjusted this to line up the columns. You can see here, right, is that we're doing a search we're doing an index scan on this index, test-only index original package. By the way, I actually lifted these all off of explain.depsays.com. It's actually wonderfully educational to look through other people's bad queries. And fun, because sometimes there was one particular query in there that had an execution time of 1.2 million milliseconds. So that's whatever it is, 120,000 seconds. I don't know why somebody waited for it to complete, honestly. It was like a day to complete this one query. But I lined up the rows column so you can see this discrepancy, right? So one of my general rules with Postgres, because I know the query planner works, is if it's within 5x or 0.2x, so within a multiple of 5, so either up to 5 times as many rows or up to a fifth as many rows, it probably doesn't change the query plan. But if it's more than that off, it will often cause the planner to choose a different query plan that can be suboptimal for the amount of rows you actually have. So like in this case, for example, we did this index scan on this, and the index scan thought it was going to return 108 rows, whereas it actually returned 10,000 rows. And given that it's actually returning 10,000 rows, so basically 100x wrong, it might have been faster to, say, use a bitmap index scan. Now, there are a number of reasons why these can be wrong. Now, in this case, the index condition is we're matching package ID on another table against package ID in this one. Now, there's a couple of reasons for that to be wrong. Number one, your statistics are out of date. You need to run analyze. You need to maybe increase the number of samples we collect per table, alter table, set statistics, et cetera. That's one of the possible reasons. Another possible reason is the column correlation problem. That is, we're already filtering on another table, and it's hard for Postgres to estimate which rows from this table match how many rows from this other table. That's a classic database problem, and sometimes there's nothing you can do about that. Other reasons statistics can be wrong. Actually, these are mainly the two reasons why you've actually sort of got stuff wrong. But so anytime you see rows that have this much of a mismatch, it's worth trying other stuff to see if you can update the statistics, if you can make queries faster. Another thing to actually look for is time-consuming loops, which is often you look at some of these things, you say, oh, it only took 0.03 milliseconds, who cares? Well, actually you do care, because it actually ran that particular loop 11,000 times. And it's feeding up to this nested loop, and the thing is, it assumed that it was only, so here we've got the nested loop estimate of 77 rows, where it actually did the loop 11,000 times, which is a lot more than it estimated it was going to do it. So basically 11,000 round trips to that particular index. And why that's important, is that then it can then lead to higher up things taking a longer time. Wait. Do I want to actually, hold on. OK. Another example of a sort of special case, but one that is often catastrophically bad when we run into it. Now, this is a huge, long query that runs off the screen. It's not important for you to see most of it. What's actually important is for you to see this factor called the response from what's called an abort-early plan. And what an abort-early plan is, Postgres, the planner estimates, and it says, hey, I'm going to actually try doing a scan over this large object, a huge index scan, a huge table scan, because I know that the user only wants 20 rows, and I think I'm going to find the first 20 rows really quickly and be able to abort that scan. When the planner is right, that can speed up your queries a lot. When the planner is wrong, it can make them really freaking slow. So the abort-early portion, the thing is here, we're doing a nested loop semi-join to get our whole mouthful of join types in here. So a nested loop semi-join between these two things. And one of the things they actually notice here is, let's get down to the cost. You say, hey, wait a minute. Costs are supposed to accumulate upwards. So the costs are cumulative from one node to the other. But here, we have a cost of 9 million for the nested loop semi-join. But then our total cost for the query is only 2,600. How can that possibly be? Well, the answer is the planner is not expecting to complete the nested loop semi-join. It's expecting to abort that early. Here's the problem. If it's wrong, then you've suddenly adopted a plan with a cost of 9.5 million, which will mean an attended time of maybe a couple of minutes to return the answer to this query, instead of the couple of seconds it would have done from, say, a different plan. So that's another one of your sort of special cases of looking for what's wrong in the explain plans. So I don't know why. Sorry about that. So one of the things you can actually do here is, so your sort of interaction here for using explain to query plans is you run your explain, then you change a parameter or stats. So we've got this whole set of enable parameters. You know, enable nest loop equals off, enable hash join equals off, enable bitmap scan equals off, that sort of thing. These are not meant to be tunables in Postgres.conf. These are meant to be for you to mess around with query plans to say, hey, is there a possible better query plan for this? Because sometimes there isn't. Sometimes you just have a terrible situation. The planner is actually doing the best it can. But sometimes it could have a better plan. So you say, okay, this nest loop is really slow. It's doing 110,000 loops. Let's force it to do some other kind of join by doing enable nest loop equals off. Or let's update the things. Let's change the number of statistics samples we have. Alter set statistics to 1,000. Then do analyze, collect more samples. Maybe we get better stats. We're still not getting better stats. I'm actually going to knock around the stats by manually setting some of the stats, particularly indistinct, which estimates the number of unique values in a row, in a column. And then I'm going to run explain again to see if I get a better query plan. So here's actually an example. That previous query plan that we had with the abort early plan gone wrong, I actually went through all of those steps. And it turned out that what I needed to do was manually fix indistinct to be a better value than the Postgres' estimate, which was an order of magnitude off for both tables. And then when I fixed indistinct and I ran explain again, I got this better plan that does not involve an abort early and that executed a lot faster. I executed in about 0.1% of the time of the original plan. So that's our basics of explain. Hopefully a little better understanding of how to read explain. And we have some time for questions. So questions? Yeah, so with partition tables, you actually see a lot of the append stuff. Let's actually, I don't have one queued up here. But you see, this is what explain.depsays.com history is good for. So let's actually, poke around. Taha, you want to ask your question while I'm poking around?
Yeah. My question is, if we have some queries to where you're passing parameters to, like sort of like what people write in Java,
Mm-hmm.
and then the parameters for executing the queries are going to be bad.
Yeah.
So now, how do you explain that on such an environment?
Yeah, that's a little challenging. So the question was about when you have prepared query plans, how do you actually test the prepared query plans? And that's a little bit problematic because we don't actually, explain doesn't provide a way to actually test a prepared query plan because it expects you to fill in the values. So here's what happens with Postgres, is if you send a prepared query plan like JDBC does, Postgres does a generic plan based on that, based on having sort of average values for each of your placeholders. The problem is that sometimes that generic plan isn't a good idea for the actual values you're going to pass. So one of the things you may want to look at is what does that generic plan actually look like? And I don't actually know a good way to do that. Because explain won't do it. Explain won't let you actually put in placeholders. So I don't have an answer for you there. It's a tool we ought to have, but we don't. More questions? Oh wait, actually I was going to do your, so here we have a partition table actually. It didn't take me much looking around to find one. So here we've got somebody who actually, I realize the text is really small, like I said. The reason why I don't use this website for slideware is because you can't enlarge the text without making it wrap in really weird ways. But this is actually here where you see the person, reason the person was having trouble with this query is it's hitting all the partitions. That's all of their partitions, and then it is doing this append to bring all the partitions together, and that's this append step right here. So that's an example of a partition plan. And so one of the things you often want to check if you have a partition table is, do your explain plan and say, hey, is this only hitting some of the partitions, or is it hitting all of them? Because if it's hitting all of them, that's probably a problem. So we have time for one more question.
How do row permissions play into using index-only plans? We were talking about 9.5 allows you to do row permissions.
Yep.
Does that mean that you can no longer do index-only scans?
I don't know the answer to that, actually. That would be a good question for Stephen Frost or somebody else. I haven't been really involved in the RLS work, so I don't actually know the answer to that. Okay, actually, I can take one more. No. Nope, that's been on the to-do list forever. We don't actually take the fact that there's a foreign key into account when making our estimates. Okay, well, thank you very much.